Welcome to This Explainer. Okay, we are jumping right into one of the most fascinating, kind of invisible architectures of our modern world. Today we're tracing the evolution of digital encryption. We're going to look at exactly how basic mathematical locks evolved into these incredibly complex, totally invisible shields that are literally protecting our global internet infrastructure every single millisecond.
And that brings us to the central mystery we're solving today. How does data actually stay secure over a compromised network? Think about it for a second. The internet is inherently open, right? When you send a text, make a bank transfer, or pull up your healthcare records, that data bounces through dozens of random routers and servers across the globe that you absolutely do not control. So if the network is basically public, how do we keep our private lives truly private?
Okay, let's dive into this. Here's our roadmap. We're covering 1. The magic of encryption, 2. Symmetric, the single key, 3. The key distribution problem, 4. Asymmetric, the digital mailbox, 5. HTTPS, the hybrid solution, and finally, 6. The future, homomorphic encryption.
Section 1. The magic of encryption, transforming the readable. This is the fundamental goal of all data security. At its core, encryption is really just a giant mathematical magic trick. We start with what cryptographers call plain text. That's your readable stuff, like an email to your boss or a password. Then, using some heavy-duty math algorithms, we transform that plain text into ciphertext. And ciphertext, it's just unreadable gibberish. It looks like absolute nonsense to anyone who might intercept it. The only way to reverse the process and get the plain text back is if you hold a very specific cryptographic key. Moving right along to Section 2, symmetric encryption, the single key. This is the baseline technology of all cryptography. To really visualize this one, just picture a heavy physical safe with a singular padlock on it. You use one exact physical key to lock the safe, and you use that exact same key to unlock it later. That's the core principle of symmetric encryption right there. It uses a single, shared secret key for both locking and unlocking the data. Simple, right?
Now, within this symmetric approach, we generally see two main flavors. First, you've got block ciphers, like the global standard AES. These take fixed chunks of data, say 128 or 256 bits, and encrypt them all at once. AES is an absolute beast when you have the hardware for it. Then we have stream ciphers, like ChaCha20. These encrypt data continuously, basically bit by bit, which makes them incredibly fast for software, mobile devices, and the modern web. Both are super rigorous, but the major takeaway here? Speed. Symmetric algorithms can process massive data sets unbelievably fast.
But wait, that leads us right into Section 3, the key distribution problem, or, honestly, the fatal flaw.
Because, look, if symmetric encryption is so blazingly fast, why aren't we just using it for absolutely everything? Well, it comes down to this one massive headache. How do two people establish a shared secret key securely over a network that's already compromised? If I want to send you a secure file, I have to give you the key to the safe. But if you're on the other side of the world, I've got to send that key over the open internet. And if anyone is snooping on the network, they just snatch the key as it goes by. Game over. Once they have it, the whole system is entirely broken. This was a huge crisis for early digital communication.
Which paves the way beautifully for Section 4, asymmetric encryption, the digital mailbox. This was the triumphant breakthrough we needed.
Now, what's really interesting about this approach is that instead of one shared key, asymmetric encryption uses a mathematically linked pair of keys. Think of a blue digital mailbox on the street. It's got a public slot where absolutely anyone can drop a message in. That's your public key, and you can share that freely with the whole world. Anyone can use it to encrypt a message for you. But, and here's the magic, the mailbox has a solid steel door at the bottom, and only you hold the private key to unlock it. You never ever share that private key.
This dual key setup is powered by some seriously wild math. There are a few heavy hitters you should know. First is RSA, which gets its security from how insanely hard it is for computers to factor giant prime numbers. Next is ECC, or elliptic curve cryptography. Actually, this one's really cool because it gives us the same security as RSA, but uses way shorter keys, so it's perfect for our smartphones. Then there's the Diffie-Hellman key exchange, which is just an elegant way for two remote computers to generate a shared key over a public network without anyone being able to intercept it. Oh, and this framework also gives us digital signatures. That's where you sign something with your private key, and the world uses your public key to verify it. It proves, without a doubt, that a document came from you and wasn't tampered with.
Okay, let's summarize the trade-offs real quick. Symmetric, one key. Asymmetric, two keys. The sharing challenge is a huge nightmare for symmetric, but completely solved by asymmetric.
But here's the catch: speed. Symmetric is incredibly fast. Asymmetric, on the other hand, is computationally intensive. Crunching all those giant prime numbers and elliptic curves takes a lot of processing power. So asymmetric is actually way too slow for things like streaming an HD movie or downloading massive files.
And that sets us up perfectly for Section 5, HTTPS, the hybrid solution. We needed a way to connect the dots and grab the best of both worlds.
And this brilliantly illustrates how modern apps actually secure the web dynamically. When you go to a secure website, TLS, Transport Layer Security, kicks in. Step 1 is the asymmetric handshake. Your browser and the server do that slow, secure, asymmetric math to authenticate who they are using digital certificates. They basically use this super secure but slow channel just long enough to safely agree on a shared secret key. Once they have it, boom! Step 2, the symmetric session. They immediately switch over to that blazingly fast symmetric key, like AES, for the actual high-speed data transfer. It's literally a perfect tag team approach.
By the way, these exact concepts are what make end-to-end encryption, or E2EE, possible. You use this every day on apps like Signal or WhatsApp. With E2EE, the keys are generated and stored exclusively right there on your device, not on some company's massive server. The server is basically just a blind messenger. It routes the jumbled ciphertext from point A to point B. But because it doesn't have your private keys, there is literally no way for the company hosting the data to read your messages.
Let's wrap up with Section 6, the future, homomorphic encryption and beyond. Because as computers get faster, our cybersecurity has to level up too.
Right now, there are two massive academic standards evolving to protect our networks in the future. First, post-quantum cryptography, or PQC. The community is actively standardizing these really robust lattice-based algorithms to make sure our current data can't be cracked by ultra-powerful quantum computers down the road. But the second one, and honestly the most mind-bending, is fully homomorphic encryption, or FHE. Listen to this, because it's a total game changer. Fully homomorphic encryption allows cloud servers to perform data analysis on encrypted data without ever decrypting it. Think about how crazy that is. Normally, to process data in the cloud, you have to briefly unlock it back into plain text so the computer can read it. But FHE lets the server do math on the ciphertext itself. It's like having a worker sort files inside a pitch-black room without ever turning on the lights or opening the envelopes.
So, what does this all mean? I want to leave you with this thought. What are the implications of a cloud AI analyzing highly sensitive medical data without ever actually seeing it? Imagine an AI scanning your MRI or processing your DNA, while your data remains 100% locked down from the second it leaves the hospital. The server doing the heavy lifting literally never converts your files to plain text. That is the wild, incredible future of privacy we're heading toward. Thank you so much for hanging out with me for this explainer today. I really hope you found this as cool as I do. Keep learning and stay secure.